Alright, welcome to another Swift Coding episode. It's been a while. Today's episode is going to be about voltage, power, amps, and wattage, and introduction to power in a circuit. This is going to be the first episode of a series, so let's get right into it. Power and electricity, we identify them as the same thing in a circuit. We can have a battery with a plus and a minus terminal. The minus terminal is usually flat in a 1.5 volt or a AAA or a AA battery. The plus side usually has a little knob on it. We have protons and electrons. Inside of an atom, we have the nucleus, and then we have the rings, the valence shells around the nucleus. Inside of the nucleus, there are little neutrons and little protons. We identify protons as positively charged and neutrons as just neutrally charged, no specific bias towards any charge. And in these outer shells we have electrons, and these electrons are basically the power source. This is basically the electricity that runs components. So electrons are negative power, and when you see electricity, or if you zap yourself, that's basically electrons, trillions of electrons going from a power source to your finger and zapping you and going through your body. So we have electrodes inside of this battery. There are billions and billions of little electrons in the negative, and for the positive electrode we have billions and billions of protons. Now say we have an LED. The wire goes from plus, goes all the way down to minus. Say we have an LED which looks like this, with a little zigzag to show that it's a diode that emits light. How can we get electrons to move from this side all the way through the plus side? Well, here's how we do it. There's a little mistake. If electricity is coming from the negative side, we really want the diode to be going this way instead. So how do we get electrons, the electricity, to move? Because electrons move around the atom, but nothing else. It just moves, and it's pulled towards because it's attracted to the protons. How do we get the electrons to move? Well, simple. If we have a conductive wire from the negative terminal to the positive terminal, electrons, which are negatively charged, and protons, which are positively charged, it attracts the electrons through the electrically conductive wire, and makes all of the trillions and trillions of electrons go through into this diode. And when it comes down to the positive terminal, it matches up with a proton, and essentially what happens when an electron meets a proton, you would think it turns into a neutron, but no. We identify it as it not existing, because the electron crashes into the proton, and our atomic science understanding, our subatomic particle understanding, isn't too amazing, so we don't actually know what happens when an electron meets a proton for sure. But essentially, what the LED looks like is it's a little bulb, and there's a wire going through and out. Now, why is there a shorter side and a longer side? Well, let me tell you. There are two sides to an LED, and you're probably going to see this in nearly every single LED you'll ever see in your life. There's an anode and a cathode side. Cathode is the longer side. The other way around. Cathode is the shorter side and anode is the longer side. Anode is what we will be calling positive terminals for anything. This is the anode terminal of a battery. This is the cathode terminal for a battery. This is the anode terminal for an LED. This is the cathode terminal for the LED. So basically, electrons go through into the cathode side, through here and out. Now, this lesson really isn't about LEDs, but the reason why it lights up is because when electrical current, which is the flow of electrons, goes through the LED, this is still a wire, there is a chemical inside of it called gallium phosphate. It doesn't need to be gallium phosphate, it can have any other second atom, but the main one is just gallium. So we can have gallium phosphate and a lot more chemicals to put onto this wire. Electrical current goes through, depending on what type of gallium, you'll get a different color, but gallium phosphate, for example, when an electrical current goes through, it emits blue light. Now, we need to learn some theory about electrons and just power in general, because obviously there's a lot more math than actual infrastructure. So we go by a few laws. There's just a basic power law. Don't know who invented this, but it's just the power law. There are three different aspects of power. We have W, V, and A. We also have an Ohm's law, which contains V, I, and R. Power law, it's just the relation between voltage, wattage, and amps. Wattage equals voltage multiplied by amps. Voltage equals amps divided by watts, and amps equals volts divided by watts. I'm just abbreviating it when I'm saying watts or volts or amps. The real name for this is amperes. Volts is voltage and watt is wattage. Watt is more broad, a more broad description for something like a generator or something, where you don't really care about the amps or the voltage. You really just care about how much electricity is going to come out and whether it's lethal or not. Mostly you're really going to see this on generators and stuff that could probably hurt you. Voltage is the amount of electrons and the force of electrons in electricity. So let's analogize this as a hand slapping you. Voltage we can think of as how fast the hand slaps you. We can think of amps, which is current, as how many times it slaps you, or how big the hand is. How big the hand that is slapping you is. So, since current is the flow of electrons, and say you get zapped, depending on the current, it determines how far electricity could probably conduct through your body. And the reason why people can survive 10,000 volts from lightning is because it actually has no current. It's just a big bolt of lightning that zaps a large area of your body, but isn't enough to conduct through your entire body, because your body is 70% water, which does not conduct electricity well. So, with enough current in electricity, say we have 100 volts. 100 volts is probably enough to really hurt you. But if it's static, which is just the word for not moving, it probably cannot hurt you that much as if it actually had, say, 100 amps. If it had 100 amps, it could probably reach your way through your skin into your heart and cause heart failure. So this is the power law. Amps is for current, which is the flow of electrons. Volts is the force in electrons. And volts and amps really depend on each other to make true electricity that moves through a wire. You need volts for amps, and you need amps for volts. Without amps, volts is just static and really doesn't have too much of a use. And without volts, amps, what is there to flow? What is there to move? If there's no force of electrons, if it goes through an LED, there's no volts to light it up. You're just flowing electrons. There's no electrons there, essentially. Now let's move to Ohm's law. Ohm's law is the relation between voltage, current, and resistance. Now you might have heard resistance in 8th grade systems class from the word resistor, and a resistor, which is labeled like this in on a circuit diagram. A resistor is what, depending on what scenario, it can either delay current or delay voltage. And when we are talking about a resistor in a circuit, say we're talking about a resistor in a circuit for a home, for example, a resistor could potentially be the charger for your iPad or a phone, or it could even be a light bulb, or it could be a TV, where the power diagram for your entire house labels resistors as things that take electricity away. Now, no home diagram, no successful home circuit diagram will have a resistor that's so powerful that it takes up all of your electricity. It spreads it evenly between all of the things in your house. Say your computer, say you have an outlet and you connect an extended outlet, one with a lot more ports, and you connect 4 different extremely power consuming computers. Chances are, depending on how much power your house gets from its power source, which could be a mile away, 2 miles away, 100 miles away, depending on where you live, some of those computers might not be getting enough computer and might just black out because it's not getting enough electricity, because the standard outlet is 240 volts. We divide that by 4. Most computers cannot run on 60 volts and require 240 volts for maximum performance. So, although your laptop might run on 60 volts, it's probably going to be extremely slow. So, a resistor, in most cases, delays voltage. But if it's in a parallel system, then voltage is fixed, but current isn't, and it delays current instead. So the actual Ohm's law, the actual math for it, is V equals IR, and we can algebraically transpose this into different equations. For example, I equals voltage current equals voltage divided by resistance, or resistance equals voltage divided by current. And we can use this to solve many problems. For example, say we have a power source here that is 20 volts, and it goes through 10 ohms. What is, in this point, V0? Well, we can use this. Let's zoom out. V0 is equal to IR. But what is the I? We don't know the I, we only know the R. So we can transpose Ohm's law to find the current. I equals V divided by R, voltage divided by resistance. We have the resistance, for example, 10 ohms, and we have the voltage, the starting voltage, 20 divided by 10, and we can get 2 from this. But 2 what? 2 apples? 2 bananas? You've probably heard your math teacher say that. Amperes is the unit for current. We have 2 amps. So now we can find V0 at this point. V0 is equal to I multiplied by R. We have I now, which is 2 multiplied by 10. And we have 20 volts. So basically why we got 20 volts after is because it actually delays current in a series. In a diagram, there is series resistance and parallel resistance. In parallel resistance, you're going to get the voltage be different, and series, you're going to get the current be different. Okay, so that is the end of this video. Thank you for watching.